Good morning.
Good morning.
Morning. So we can wait a little bit more time for other people to join. Good morning, Anna.
Hello, Patricia. Good morning.
So we're waiting for let's wait the typical Berkeley 5 for
Sure.
more people to join, and then we can start.
Absolutely.
So for today, so as more people are joining in, good morning. But for today, I wanted to bring up very quickly the topic of the Global Summit. So, so are you guys? So is everyone going to the OCP Global Summit?
And I'll be there. Oh,
I'll be there.
Yeah, of course.
Okay.
You
But
mean
we
the Global Summit, OCP Global Summit?
yeah.
Okay.
Yeah, so because our next meeting is on October 15, which is during the Global Summit. So what we can do is try to set up something so we all meet in person. So we can kind of talk in person and see each other in real time. So I think that the agenda is up already, and it seems that it's going to be very busy, but we can try to set up sometime during maybe lunchtime or maybe break time. So yeah, let's try to figure that out. You guys can let me know your preferences, and we can try to do that.
Yeah, I think there's 2 breaks of 15 minutes and there's 1 hour for lunch. And then other than that, we really packed in the program from 8 a.m. to 4 p.m. So I think lunch might be a better bet than 15 minutes of coffee break. So
Yeah.
yeah,
And
I'm
then,
expecting people are going to be in line getting coffee. So lunch might give you a little more time, Patricia.
yeah, okay. So we can plan lunch, or so plan lunch is. I've never been in a summit, so lunch is provided on site, or we have to go out.
No, lunch is provided. There is lunch
Okay.
there. Yeah.
Yeah, well, so we can try to
Yeah,
meet.
we just need to sort of find a table where everyone can meet. I think that might be your biggest challenge, to find a common an area where everyone can sit.
Yeah, okay. Or we can try to plan dinner, like go for dinner and have something as well. So let's see how I'll send an email and you guys can let me know how you feel, and then I can, send an invite so you don't forget about it. Okay, so that's there for the plans for the so I'm going to cancel our calendar invite for next meeting, but I'm gonna put another one. I don't know when, so we can meet in person. So I think we can start. So today, well, we have been talking about HPC in the last couple of meetings. So we have some ideas of kernels that are of interest for the HPC and the scientific community. But we haven't talked a lot about artificial intelligence in this context. So that's why we invited Anna here to join us and talk a little bit about her work with artificial intelligence and FPGAs and how it applies in the context of the National Lab and scientific computing, which is quite interesting. So I think I'm gonna leave it to Joanna, and you can start.
Yeah. All right. All right. Hello, everyone. So my name is Anastasia Budko, and so today's a little bit. It's been a little bit chaotic. We were hoping that our colleague Nirmal would be here to present some of our newest result, like of the last week, but he was not able to join. So I will be giving your the results and like the results of the last month instead, and not of the last week. But I hope you will still be able to enjoy this. Okay, so let me share my screen. All right, slideshow. Let me know if you can see my slides.
Yeah,
Yeah.
for some reason it looks very smaller than what.
I knew it's gonna happen. All right, let me try to fix that. That's because you know, Patricia, how I have the same screen as you do.
Oh, the big one, yeah.
Okay, let me see if I can maybe put it on the smaller slideshow here. Does it look better?
It's not showing. Maybe it's on the other screen.
It is right.
This one seems readable for us. So if you can't get into presentation
saw
mode,
it?
maybe.
You saw it, right?
No, we don't see the slideshow. We see the slide set. Not the presenter mode, basically. Or maybe the presenter mode is on the other screen or something.
Oh, okay. Let me unshare. Let me. I know what I'm doing. Okay. Let me unshare, and then I'm gonna start the presenter mode, and then I'm gonna share again, but a different screen. This click. Yeah. How about now?
Yeah, no, it looks good. Yeah.
Okay. All right. Sorry about that. Okay. All right. So so today I'm going to talk about the scientific edge computing and AI-enabled object tracking for radiological source subject attribution and FPGAs. And it's a very mouthful and long title, I know, but I'm going to try and like cut it down to like smaller kind of topics and explain how it's all tied together. And then I will have a small piece of like quantum computing in the end, because that's also how we apply AI on FPGAs in our group. So, all right. So I will start by explaining a little bit more about the scientific age computing and how we ended up. So by the way, I'm from the computer architecture group, the same computer architecture group as Patricia. So we're doing different computer architectures, and so how we ended up in the scientific edge computing environment, and how we actually ended up in working with people in nuclear science. So this is the project from 2020, and we ended up working with the nuclear science and the 5G, which is a very interesting combination of fields. And when people ask me what you're working on, and I say nuclear science and 5G, and people sometimes get confused because this is very untypical combination for me. So I'll try to explain how it all tied together. So back in 2020, we had this 5G enabled energy innovation workshop from DOE, where we all got together and tried to see how the 5G technology can bring in innovation to science. Of course, we do have it in our phones, and we use it every day, but in the scientific community, it has not been applied for experiment. So we had those 5 different trusts where we, or working groups where we discussed how the 5G can bring innovation. And it was digital continuum, edge computing, scientific instrumentation, extreme environments, and testbeds. And in our group, and in our team, we kind of had touched 3 of those particular topics were edge computing, extreme environments, and testbeds. And well, edge computing is something that I will be talking about today in testbeds in particular. And extreme environments is because, nuclear science and extreme environments is something that is, very closely related. In terms of scientific use cases, nuclear science, it is a very relevant use case, and they do have obviously scientific use cases where they develop some materials and weapons, etc., etc. But they also have use cases that are more like city scale or urban network cases where they have multiple sensors, a network of sensors, and they kind of drive those. They distribute those sensors across the field, which is, let's say, an urban environment in the city, and they try to, and this is the problem, they try to identify if there is a particular anomaly in the field, and they need to track it, identify, and understand if this anomaly is something which is normal, or if it's actually dangerous. And it's quite hard because in nature there's always something happening, and to trigger an alarm, it's very easy, and to separate the background noise from something really alarming is very harder. Classical algorithms not very accurate. There's always false alarms, and this is where the AI is going to be coming later in my talk. So this is a very typical kind of flow for the algorithm. This is what the object tracking in my talk and in my title is coming from. So this is kind of the flow of the processes of the kind of a workflow. So this is what the nuclear science use case is. And in terms of the 5G, obviously, because it's like the sensors are distributed in the environment, so the wireless network connectivity is very important for them. So the 5G technology brings them kind of new capabilities. It's a new opportunity to directly integrate the different contextual information from physical sensors, and it can also improve the detection sensitivity, and the localization performance. So with this new technology and this new capability of the wireless network, the edge compute also is coming into picture, because when you change something, some parameter in the system, you need to change another parameter in the system. So the edge compute component needed to be addressed as well in this big picture of the entire experiment. So we were working on the edge compute component. And so it's been like a 5-year project. So we started with a very small and a kind of lightweight testbed. We call it Tower. So it's written very weirdly, but it's pronounced Tower. So this is kind of a previous work. So we built this testbed. So this is our team. So we had people from ESNet, who's been responsible for the networking part. Us from the CS department, who've been responsible on the edge compute part, and people from the nuclear science department who've been responsible on the the nuclear science part. So in the testbed looked like we had the gamma detectors, or the sensors. So they have different kind of the sensor. They have lidars, they have video streaming cameras. So we had this very simple gamma ray detector in this particular example. Then we had a very small Raspberry Pi as an edge device, very simple one. obviously that's not an FPGA in this particular case, but that's just a demonstration for you guys. And then we had this Raspberry Pi had a 5G development kit on top of that that allowed us to connect it remotely to the 5G base station, and we had a Firecell 5G base station, and then we used regular connectivity to go to the cloud, and then we use different AWS services to do like the kind of message passing and visualization of the data that we collected. So it's not really important, and more like a visualization part. So we had the demo of this all set up last year at supercomputing. So that was a DOE booth. So a fun fact, we had so because it's been a demonstration of detection of an alarm, detection of the nuclear source, and we had an algorithm that's been running. So we had an algorithm that's been running on the Raspberry Pi. So an algorithm was receiving the observational data from the sensor, and the sensor was supposed to detect some source of some gamma source, and I brought all of the hardware to Denver, and I was like, I cannot bring any dangerous radiological source with me to Denver, obviously. So we filmed a video of a student filmed a video with a siesta plate, which is a well-known source of radiological dangerous material from authorities, and this is what we've been demonstrating at the supercomputing, and so the demo was, if you're interested, I can dig out my video. I still have it. So the demo is that you approach the plate to the sensor, and the algorithm that is running on the Raspberry Pi. So everything is green. If you can see on this picture, everything is green. Then if you approach it, the algorithm would detect, the sensor would sense the data, and the algorithm would detect an alarm and say, hey, there's something dangerous close by. So, but the fun fact is that when it's also some sort of it's not an AI, but it's very simple algorithm, but it kind of collects the background data, and then it builds the model, and then for the period of time. So we had like a 5-minute training period, and then John Schalf wanted us to check if there was a Cray machine in the DOE booth from 70s, and he said that this Cray machine had some material that used to be dangerous. And he said, hey, can you guys check if your detector can detect anything? And I was like, yeah, sure. And I placed my detectors on the floor, and all of a sudden all of my algorithms just started to kind of show everything red. So apparently there's some nuclear material in the floor, in the concrete on the exhibition floor in Denver, in the center, in supercomputing. But then I was freaking out, but then the nuclear science folks told me, hey, it's okay, don't worry about that. We're using very simple algorithm, and this is actually what the problem is with all of this removing the background noise, and that's very typical to detect something like that. And this is what the problem is in science. So that's the fun part. So that's the demonstration. That's how how the all kind of everything works in the picture. So where the FPGAs are coming from, finally coming to the FPGAs part. All right, so So this part of the work is where the AI capabilities on the modern FPGAs are. So obviously the Raspberry Pi that we have in this, in this setup, and first we have only one sensor in this small example setup, and ideally we would like to have multiple sensors, and we would like to scale it up to multiple sensors, and we would like to have more advanced algorithms and more advanced devices at the edge, that this is where the FPGAs are coming from instead of the Raspberry Pis. So this is a short summary about what we've been looking at and what we can, what we can consider as the AI capabilities on the modern FPGAs. So this is a short kind of summary. So we have, I kind of summarized this in three different categories. And each category is rated in four different kind of parameters in customization, in terms of customization, performance, energy efficiency, and usability. So the first one is the programmable logic, which is the fabric itself, right? The FPGA fabric, where you are supposed to design your own RTL. So instead of customization, it is extremely high because you are designing your own design. So you can do pretty much whatever you want. You can design your own processing elements, your own logic, and it's the highest you can get. In terms of performance, it's moderate to high, and it's all like all of the rating is obviously kind of arbitrary, and it depends on the complexity of your design, and and in terms of the complexity, depending on how complex your design is, the timings and the frequency can vary. So the energy efficiency is also variable because again, depends on the complexity. And it's generally high because of the flexibility. And the usability obviously is extremely complex because you need to have a very deep understanding of the hardware design, and have a very long training curve to be able to do this. Even with all of the modern languages and HLS and so on and so forth, you still need to have experience using all of that. So the next one is something that very typical. And most of those examples I'm taking for was this AMD new series of FPGAs that they call Versal AI cores, or they have a couple of new ones, but this is the VCK 190 board. So this is an AI engine, which is the chip that sits on the FPGA. Which is a sort of like an AI accelerator. So the customization is obviously limited because that's already a chip with a particular architecture. And well, it's within the scope of AI and machine learning operation. The performance is high because it's optimized for the parallel AI operation. Energy efficiency optimized for for AI workloads. And usability is moderate. It is easier to use with the AI framework, but still it still requires kind of a lot of understanding of the AI models. But I say that it's coming mostly not from the AI models understanding, but from the workflow of Xilinx itself. That's the most complexity where it's coming from. And the last one is what they call the DPU, or the Deep Learning Processing Unit, which sits also on the programmable logic side, on the fabric itself. But they designed kind of something in between the AI engine and the programmable logic, so you don't have to design your own RTL. So you design everything, I think, in I dare say C++ or Python, but when you compile it, it kind of generates or HLS, it generates you the RTL. So you don't have control over what you're designing at the end, but it is the customization is limited to a deep learning operation. So it is designed for the deep learning. So and the usability is high. And it is designed for rapid deployment and development for deep learning operations, and they have those APIs. So the results I'm going to show you.
Hey, Anna.
Yes.
So the training will be done in the data center, right? I mean, you may not have to train in the edge, or do you still train at the edge?
Yeah, no, the training needs to be done somewhere else. Yes. Yeah.
Okay.
Exactly. Yeah, you're right.
Okay. Got it. Thanks.
Sure. Yeah, so the results I'm going to show you right now are exactly on the GPU. And for the training part of this result, we took the models that are provided by the Xilinx. So we didn't do the training itself for them. But for the newest model that Nirmal was supposed to be showing today, he's been doing the training on I think on Perlmutter or on the Labyrinthine supercomputers that we have. So yeah, so that's a little bit of the details on the GPU for the yeah, well, I already told you what it is. So the cores sit on the programmable logic. So they communicate. So the communication is coming from the PS side, which is the ARM cores in the DDR memory. So yeah, so this is kind of the off-chip. Oh, I'm sorry. The communication with the PL logic. Yeah, so some of the experimental results that we got is the performance is the frames per second. So we had 3 benchmarks that we run is the YOLO V6 face detection and vehicle classification. So this is something that would be useful for the tracking problem for the nuclear science that I mentioned. And we had up to 8 threads kind of different performance. So I think that's quite good for, especially for the vehicle classification up to like 5,600 frames per second. That's quite impressive when given that it's sit on the PO. And in terms of the power consumption, those are some of the results in terms of the power consumption, again, on the same benchmark. And we have, I think the highest we got like a 50 watt. Yeah. So
again, this power consumption, you're looking at it more from a training perspective or a inferencing perspective? I mean, where would you deploy it? Because that will matter, right?
This is the inference, yes.
Inferencing side of it?
I'm sorry?
Yeah, because face detection and vehicle classification should be all, I think, inferencing.
Yeah, it's the inferencing. Yeah, exactly.
So 30 watts, I don't know. Does 30 watts, is that reasonable for y'all, or is it too high or too low?
It's reasonable. It's better than before. This is what I would say. Especially for the YOLO with 6. So we had the different architecture set up for the project with YOLO. Well, it was YOLO V7, but let's say it's a comparable benchmark. And yes, it's at least twice less power consumption than what we had before. Yeah.
And how many FPGAs? Is it like one FPGA or
it's just one FPGA? It's just one FPGA.
One FPGA. Okay.
Yeah. Especially compared to GPUs, it's just like it's so much better.
Okay.
So yeah. So that's just preliminary results. Again, I'm very excited. We got much further for the over the last months, but again, that's just first result. All right, so that's it for the edge compute. But I just wanted to show you, because we're using the same FPGAs for multiple use cases. We have, and this is the, again, this is the DPU part, but I also have some use cases where we use the AI engine. And I forgot to mention that the AI engine can run up to one gigahertz, 1.2 gigahertz or something like that. So sorry. And this is the quantum use case, and I like to say quantum is also an edge compute, just to it's the quantum people don't like it, but it's okay. At the Berkeley lab, we have something that is called the Advanced Quantum Testbed, which is also a test bed for the quantum folks. We have this is full stack test bed for superconducting qubits. And I'm also part of this test bed team, where we have for the test bed, we have the entire full stack of development. We have people from material science who are working on, materials and at low level, people who are designing the QPUs at, the qubit level. We have people in molecular foundry, and then we have people who are working with the fridge, the delusional refrigerator, and people like us who are designing the control hardware. And with the current technology, without going too much into the details, there's the current technology. Most of our control hardware sits at the room temperature. And in this picture in particular, this is our actual test bed, and our hardware sits on the left, and all of the blue cables is what the control signal is coming and going back to the fridge with the data. So the problem that where we're using, and the control architecture itself is happening on the FPGA. So our team, we designed our own control, the entire control architecture on the FPGA. It's called Cubic. It's open source. You can check it out if someone is interested in. There is a small piece of this architecture that is an AI component. So I will just briefly explain why it is important. So this is a very typical way how quantum people describe their algorithm. That's called the circuit. Each block, each square block is an operation that is applied on top of the qubit. So the problem with superconducting qubits is that their lifetime, which is the big arrow, is very short, and the operation, which is the small arrow, is very short, is even shorter than that. So the small error is around 15 to 20 nanoseconds. So that, and if you have a lot of qubits, then brings a lot of pressure on the control hardware, how quickly the control hardware needs to deliver the control signals, right? So it means that within the 20 nanoseconds, the control hardware needs to issue instructions and make decisions and so on and so forth. So this particular example is called mid-circuit measurements, where a control hardware needs to perform, issue instructions and perform operations on top of the qubits, measure the state of the qubit, and then, depending on the state, apply a conditional operation. So it's a conditional branching. So, and it's called an enabling mid-circuit measurement. So because of this very short operations, the control hardware, which is an FPGA operation, needs to be very quick. So, and it's the measurement itself called state discrimination. And so the slogan for that I call "We do not discriminate unless it's a quantum state." So the process of state discrimination is quite complex. So it is without going too much into the details. And this is kind of the blobs that you see on the screen. There is those clouds of points. So the algorithm is supposed to separate them, and depending on kind of how many points in each blob is, the state would be 0 or 1. And that's called the state discrimination. In the past years, until the previous couple of years, people were using something that is called Gaussian mixture model to determine, or just drawing the line, or very simple classical algorithms to define if there's a 0 or 1 for the state discrimination. But first, it's slow. Second, it's very not accurate. And then this year, a person from my team designed this FPGA algorithm based on the neural network, where they put this entire lightweight neural network on the FPGA and design it such as that it allowed to perform a very, very quick state discrimination within the time frame. So it would allow us to do this very quick decision making and allow this conditional branching and mid-circuit measurement experiment with the quantum testbed that we have at the lab. So yes, and the neural network here, it performs the state discrimination in 54 nanoseconds. So it's quite quick. Well, yeah, it's quite quick. It's yes, it's quick. But because we're always looking further and we'll always try to improve, and because there's still room for improvement, we're looking into how we can compare it and scale it up. So we have ported the same algorithms, and we are porting that to the AI engine, and we have already done that, but we're kind of in the middle of testing that. So I don't have results for you to show, but I know for the fact that this neural network takes probably like 5% of the AI engine resources, which means that we can, and there's a paper if you're interested in this. So this neural network took about like the accuracy is very high, quite high, but if I increase the size of the neural network, we can increase even more the accuracy. So that's the hope. So yeah, so that's about the quantum application that we use, and but also looking into using different other AI accelerators, because there are much more. And in Argonne National Lab, they actually have more test beds that are available that we can apply and get the allocation. So that's the future work we're looking at. So that's it. That's my talk for today.
Thank you so much, Anna. This is quite interesting for us because you described very different applications using AI, and that will define different requirements for the chiplets. So if we wanted to build the same system you're building here using chiplets, we need to understand how different all these chiplets will look like, depending on the different applications you described that are quite interesting. I don't know if there are some questions.
Is there any kernels out here, Anna? Like HPC kernel? Is it similar to any kind of HPC kernels that you're using for the two use cases?
HPC kernels.
Like a fast Fourier transform or discrete Fourier transform?
So let me think about that. There might be something like that in in both use cases, especially in, okay, let me start by the last one, that the quantum It's not necessarily an HPC workload, but for the well, it's not considered HPC, but for the quantum error correction, the decoder, something that is called decoding of the error correction, is extremely, it's a graph problem, which is considered to be the problem that requires a supercomputer to be solved. So I would classify it as an HPC workload. So there was a paper last year that by NERSC people who estimated the size of the supercomputer and it needed to be that we needed to have in order to perform this operation for the quantum for the quantum use case.
I was thinking that for the nuclear use case, nuclear radiological use case, you have to go from an analog world to a digital world, right?
Yeah, that's also obviously yes. The definitely should be use cases like that, and for the FFT, I'm sure there definitely use cases like that. Yeah.
Okay. I'm not trying to feed an answer. I was just trying to understand how that, where are your bottlenecks essentially, right? If you as to scale this up, I think that's what we need to understand. As you scale this up, what will be your next set of bottlenecks?
No, there are definitely bottlenecks like that, and also that, as I said, the different sensors. I just showed you a little bit, like a very small and very simple sensors. The different sensors that provides data in different formats, and as you said, the format can be an analog data, and yes, and sometimes, and obviously now we're thinking how to integrate this edge compute even closer to the sensor, and like that's whole kind of, that's a completely different. I can talk for another hour about this. Yeah.
So yeah, so are there any other questions? Well, and I think we're gonna start discussing all these examples, and hopefully, like, all this information is gonna go into a standard for chiplets. So we'll reach out to you later on with more questions.
Yeah.
But thank you so much for joining us today. We really appreciate it.
Sure. Thank you for inviting me.
Yeah. Thank you.
Yeah, sure. I can go, right?
Yes, you feel free to stay or go. Yeah.
Okay, well,
Yeah, thank you so much, Anna. All right, so I apologize for the mess I have in my background where I'm moving today, so there is a lot of boxes going on. So I'm gonna turn off my video so you guys don't see the movement here. But yeah, so I think we have 20 minutes or 15 minutes to talk about how are we gonna move forward. So well, talking to George, or talking with George, there are two different ways we can approach this. So we can take a couple of, I mean, there are many ways, and if you guys have better, ideas and options, just bring them up, of course. So, but we were talking about, like, we can take a kernel and then ourselves kind of run it in a system and then try to do some performance analysis out of those kernels. Or we could extract the information from papers, and then when we have questions, we can reach out to experts. Or like, what do you guys are thinking?
Hey, if I can chime in. I would like to start with one good solid use case, Patricia. So that's what I was hunting around. I mean, just what I was like, some of the presentations that were given by G and John were very, very impressive. I mean, that could be itself a good starting point, but that could be others. But why not start with something that we can get a hands-on, some use case?
I think that makes sense. So I know, like I don't know if you remember, you brought up this paper with that had all the different HPC kernels, predominant HPC kernels that were out there. So that's one use case. Another one would be to tackle, for example, density functional theory.
Yeah.
It's the one that John Shah, for example, brought up, and then Tom explained a little bit more about that. But I think tackling density functional theory as a whole is a big problem. Tom has been working on that for 5 years.
Yeah, I know we have to find, no, so if you don't
Yeah.
mind, let me share my screen. Are you okay?
Yeah, of course.
Because I was just thinking, you should see my screen. So basically, I want to see if I can, there are two things that I would like to see if I can follow up from the last two sessions, right? Last two meetings. So this is the one that we have seen many times, right? The one from the Perlmutter runs, right? And so I'm trying to get it down to like specific applications that are taking a long number of hours. So I just put some sample numbers out here. Okay, this 12 hours is just a sample, but if you look at it, there's a histogram out here as to some of the jobs are running for 6 to 12 hours and running on large number of nodes. So I want to see if there is any second level detail that we can get, which is basically saying, hey, application 1, maybe there is like a highest running job in that is taking 12 hours, maybe 64 nodes, I don't know. But what's the CPU utilization, DRAM utilization, GPU utilization, HBM utilization? And also, what is the kernel on that job, right? So that's what well, then that could be a use case. Then we can say, okay, what is the challenge or problem in that particular kernel or job? Is it data size? Is it a CPU utilization? What about something should be kind of the bottleneck, right, as we scale. And so, especially if you look at the number of nodes, again, this is an example. So but there are some jobs that are running for lot of nodes and lot of hours. So I'd like to take some CPU jobs, top 2 or 3 applications that are very slow, top 2 or 3 applications that are GPU jobs that are like take very long, a lot of nodes. So that's something that then we'll know what the kernel is and what are the other challenges in that particular kind of jobs. So I would like to start building it up. So we start with the problem first, and then you try to understand what the bottlenecks are, and then you try to figure out what it could be some potential solutions.
Okay.
The other thing that also I liked a lot from John's presentation is, let me just share it. I think is this, let me see where I can find it. Yeah, I think I like this particular example he gave about kilometer scale climate modeling. And he basically showed that if you want to do like resolution of say 25 kilometers today to one kilometer, let's say in the future, that can take a very long time. It could take almost like 20, 30, 40 years, right? That's what he's showing out here. So if this is another use case that we can understand more of as to what is the application, what's the job they're trying to do, what's scenario modeling, what's the kernel, then we can say, hey, is there any way that we can kind of bring this curve in, right? Could be chiplets, could be one answer, but maybe that could be that we need to like take a very objective view at it before we start going down some direction. So, but it will be good to understand this use case, at least some of these use cases, 2 or 3 of the use cases very well. So that's my request. If we can find what's happening in the Perlmutter or what's happening in the climate modeling.
So you thinking that climate modeling is more would give you more insight than, for example, density functional theory?
No, I said that no. I mean, I said we need to get the next level of information for very specific use cases. So if you have a handful, we'll have better understanding what the problem is, right? So let's take this, right? This from the Perlmutter. Let's say it could be, I don't know, maybe it's Atlas, maybe it's VASP. I don't know what it is, because I kind of, from this, it's very difficult for me to figure out what is the kind of the challenge for Atlas, right? Or what's the kernel, what's the challenge? Is it a CPU? How many hours is running this particular Atlas job? But also I'm saying if you can break it down and say, hey, this could be an Atlas job, and that job runs with this kernel. It runs for 12 hours, takes 64 nodes, for example. Then we can say, is there any way of maybe, so that could be a problem, right? To say, hey, it takes a long time. And if I can run this in like 1 hour on 2 nodes, or let's say 2 of the chiplet-based systems, obviously it'd be a big win, right? So I'd take a top-down approach to this, to defining these use cases and see if there is a good solution out there.
So one way I can think of doing that is, when I was trying to work, I was looking into molecular dynamics at some point. But because basically what we're trying to do is some sort of hardware acceleration, right? Because we're talking about the specialization. So I was looking into papers that were already doing hardware acceleration for molecular dynamics. And that gave me some insight into what the important kernels are, for example. So, like just to give you that example, the majority of papers kind of convene into FFT, fast Fourier transform, is the major or more dominant kernel in molecular dynamics. So all the other steps into the algorithm were kind of relegated to software, but then they put an FFT, a 3-dimensional FFT, a hardware accelerator, to do that part. That was kind of the most dominant. Does that sound something like what you're looking for, like that we can understand the requirements to do hardware acceleration on this? Or is more about software? You're thinking about doing some like again, with the molecular dynamics example, I run molecular dynamics and I will know how much CPU utilization do I have, how much DRAM does it need. Yeah, I think that's more.
That's the use case. I said we should like gather a handful of use cases that we can handle. In molecular dynamics is that one use case. Let's pull that in. I mean, it should be in a form to say, I run this molecular dynamics use case. It's an application or it's a job, right? And it takes me, I don't know, hundreds of hours. I can only do so much resolution, like in this time of say kilometer scale modeling. You say, hey, I'm only able to do 25 kilometer resolution, but I wish I could do 1 kilometer resolution, right?
Yeah.
And it says, maybe it'll say something like, hey, a number of nodes, it takes me lots of nodes, like say dozens of nodes. And my CPU is highly utilized, or my DRAM is utilized, whatever it is, right? So what are the bottlenecks?
I see what you're saying. So I think so there are 2 ways where we can do that. Like we have to get that out of literature, papers, or we have to do it ourselves. I don't know.
I was thinking if G had already done this, it's just a question, at least for ones that be easy to get, right? I'm trying to make it simpler to get something in our hands that we can start.
So if you go
tackling.
back to the slide 10, basically what you're proposing is trying to understand each of these, in your slide 10, if you go back there,
Yeah.
try to get each of these,
Yeah, just a top 3 or 4, right? Just because we don't want to make it too elaborate, just the top 3 or 4. So if I can just say, go back to 10 and say, hey, Atlas, what are the Atlas jobs? Because I don't know from this, I cannot figure out how many nodes, how many hours these Atlas jobs are taking, right? And so I don't know what the kernel is. At least I'm not familiar with that.
Yeah,
so
no,
maybe,
I guess.
So I'm just saying, if you can able to break it up this way, because if you look at it, there's all these jobs, 21,000 jobs represented in that 21,000 jobs, 21K jobs, right? CPU jobs, and 24,000 GPU jobs represented in this data set. So it's a very big data set. So I'm trying to piece it down to what is really the biggest problem that we can take a look at and see if there is a way to kind of solve that, say 2 or 3 use cases.
Yeah. Yeah, I see what you're saying. Yeah, I mean, we can do that, but I think we have to find a way that we can distribute the job among all of us. Well, right now we're only 3.
No. So I think, Patricia,
Yeah.
I'm just like, I mean, I don't know. I'm just hopefully that's if G can, that's what I had requested to say. If you can just give us more details on the longest running job on the most number of nodes, right? And what's the kernel out there, and what is all of these parameters, all of these profiles, what is CPU utilization, GPU, DRAM utilization, GPU utilization on that particular job, then we can dig in and figure out how we take that one particular use case and maybe solve for it, right? To understand if this can be solved in a kind of chiplet-based architecture.
Okay, yeah, I see.
I'm going to start with the problem. I got to, instead of starting with the solution, start with the problem. Because I don't want to build a solution that is then looking for a problem, right? So I started the problem first, and then say, okay, this is the problem. And someone from researcher comes and tells us, if G comes and tells us, or John Schaus comes and tells us, hey, this is a problem for me. It'll take me 10, 20 years to get to this kilometer scale modeling. And I wish I can do it in like 2 years or 3 years or 5 years, whatever it is, right? Then we can say, okay, that's a problem. We can try to figure out if chiplets can be a solution for that.
Yeah. Yes, I understand that.
I mean, we can do, I said, we can do it both ways in a sense that we can start looking at the kernels, but I don't know where these kernels are going. And I don't know what the problem statement is there to say, other than that, I know that this FFT kernel is being used a lot of places, but how is it used in a job, right? How is it used in an application? And what's really slowing it down? That is, I've not been able to kind of I
mean, that's the question that we have to answer. I agree with that. So for example, like, I think one of the initial papers we looked at, they did a similar study that what they did in slide 10, where they took all these applications and they say, okay, from these applications, what are the most popular kernels? Because like here, these are not kernels, these are applications,
Correct.
For example,
exactly.
Espresso, quantum espresso is something that is used to, I don't know if this espresso refers to quantum espresso, but quantum espresso is something that is used to AB initio calculations. And then for these AB initio calculations, you need to do a bunch of you have to use a bunch of kernels in order to complete the whole calculation that espresso does. The same for VASP. And then that paper took kind of did that abstraction out of the application and said, okay, these are the kernels that are most used in high performance computing. So that's one way we look at the kernels. Then the other way is we look at an application, as you said, like we took Atlas, for example, that looks big here, doesn't matter. I mean, as just an example. We take density functional theory, we take any of these, and then we tackled in that side. I think that makes also a lot of sense, like either one or the other makes a lot of sense. But I guess what I'm hearing from you is that you think we should reach out to people that would give us those numbers, not necessarily try to get them ourselves.
Oh, yeah, absolutely. Yeah, totally.
Then,
right. I mean, because, if the data is there and the researcher saying, hey, this is a problem for me, the least I would expect to say, hey, this is a problem for me. And here, if it can even be, I don't know, this is the simplest way I could put it, because all this data is there. I mean, all this data that is there is already published in this paper, right? So if you look at the paper that talks about the CPU utilization, DRAM utilization, job duration, allocated nodes, etc., etc. Except only problem is that it's all consolidated at a high level for a paper presentation. So we need to take it down and say, hey, just start with all the data is already there. And start there, because if we start running these jobs, it'll take us a long time for us.
No, I agree.
And we may not even have like hundreds of nodes and thousands of hours, right? It's almost impossible.
Exactly.
So start with where the data is and who was able to share the data. And that could, by the way, the Perlmutter is one place, I think, looks like you have access, or we have access to that, right? But that could be other national labs also. But let's start with where we have the highest touch point.
Okay. No, I think that makes sense. So we have, we don't have, I think this is a good discussion. We should continue it next time with everyone else and see. But I think, either approach would work. Either we go into individual kernels, we go into a big problem. All of them will work. We'll have to reach out. I mean, we have to look in literature and reach out to the right person. You're gonna be surprised that when you talk with the scientists, sometimes they don't know where the problems are.
No, right, exactly. So by I'm saying
digging that information out of their brain is a little bit difficult, but yeah. So we can do that.
yeah.
So,
So that's exactly the reason I'm saying, if you can just reformat this data, when you say reformat, it's just like extracting out the top jobs out here. You know, if you see this on the paper, right? He's got 21,000 jobs and 21,000 CPU jobs, 24,000 GPU jobs. So it's like essentially like the data is already there. I'm assuming data is already there. It's already broken up by number of hours and number of nodes.
yeah.
So all you need to ask is hopefully, hey, can you just give me the top 2 jobs or top 5 jobs, top 2 CPU jobs, top 2 GPU jobs, and tell me a little bit more about the kernel, the application, the number of hours, number of nodes, all of these things, right? Hopefully it's as simple as that.
Yeah. So, well, you will be surprised.
No, I agree. But Patricia, I mean, if you want to solve, so take a real world example, because I would rather solve a real world example for a scientific community that's struggling to say, hey, this is really a pain point for me. I would like to start from that point.
Yeah.
And then back it into what's the kernel, what's the kind of the bottlenecks, and then say, hey, okay, now let's see if this is a better way to solve this thing.
Okay, that sounds good. So let's continue. Yeah, so let's continue this conversation next time with everyone, and then hopefully I'll see you in the summit.
Yeah, is it possible to send this data request out to Xi?
I mean, yeah, like you can send it out. Send it to him. You have his email, right?
And I don't. I mean, but it'd be good to come through you or George, right? Because you guys work closely with him a lot. So I can send it to you and George and see if this data can be pulled out. It's like I'm hoping it'll be just the top 2 jobs or top 4 CPU jobs or top 2 GPU jobs with these details.
Then do that. Let's do that. So just send the email to George and I, and then we'll forward it to him and see what happens. Yeah.
Yeah, absolutely.
Okay. So see you next time. Bye-bye.
Yeah. All right. Bye.